So welcome back, everybody, to the first afternoon session. The first speaker is Patrick Kidger, who's a final year PhD/DPhil student in Oxford, and he's going to talk about neural-controlled differential equations.
All right. So first of all, hello, everyone. It's lovely to be here. For those of you who don't know me, indeed, I'm Patrick. And well, let's get started. So as I probably don't need to tell very many people, differential equations have really been like this dominant way of understanding the world for like forever. And of course, much more recently, neural networks have arrived, and they're another great way of understanding the world. So you can probably guess, what happens when we have these two amazing ideas. Well, obviously what we're going to do is we're going to try and smash the two together and hope something interesting, something meaningful pops out. So this particular combination is neural differential equations. And basically it promises best of both worlds. So we'll sort of like touch on some of these points as we go through, but we get lots of things coming out of this combination, things like memory efficiency, strong priors on model space, high capacity function approximation, and lots of theory coming from both sides of the aisle. And as a result, because it's this sort of merging of very traditionally scientific methods and these very traditionally sort of, I guess you might say, technological methods for sort of differential equations and neural networks each, then we actually see applications in turn back to both sides of this sort of hybridization. So you see applications both to sort of the traditional problems that mathematical modeling has often concerned itself with, but also problems that you more typically see machine learning folks talking about. And so again, we're going to try and touch on some of these points today. So this is the program. I'm going to start off sort of talking about neural differential equations just a little bit, just in general, give you some intuition, some applications. And then we're going to look at a specific example of neural controlled differential equations, which I'll discuss in some more detail. And in particular, we'll see that these have a particular intuition. Those are continuous time recurrent neural networks with applications, and we'll look at a particular application to irregular time series. And then ever so briefly, I'm also going to mention how we can use these to train neural SDEs, although not in any great technical detail. And then also very briefly, I'll tell you a little bit about the software. So I realize obviously this whole sort of, presentation, this whole workshop, sorry, is about, rough path theory and things like that. And so this is really where these neural controlled differential equations come in, because this is really where rough path theory meets neural differential equations. So I'm going to sort of, I'm not going to be emphasizing the connections too strongly. They're a little bit more theoretical than I really want to get into today, but they are very, very strongly there. So first of all, what is a neural differential equation? I've thrown that word around a few times now. It's a very simple idea. It's simply saying that we're going to take our neural network and we're going to use that as the vector field in a differential equation. And the canonical example here is the neural ODE. So it's this, you can see here, this is hopefully a relatively familiar sort of thing to write down. It's just an ordinary differential equation. And all I've done is I've said that right-hand side over there is going to be some neural network. That's what that F theta is. I'm attributing this to Chen et al. You can actually find examples in the literature going back to the 90s, but it's really with this paper that things properly kicked off. So as I say, F theta, this is really just any standard network, and very often it'll be a feed-forward neural network. You might have seen pictures like this before. It's probably one of these that we're going to be using. And then I say why you might already be using them. That's the subtitle here. And the reason for that is because I'm going to motivate this as a sensible thing to be doing by giving you a very classical example of a neural, in quotes, differential equation. And that example is the SIR model. So I don't know if folks are familiar with this. This is a classical example from mathematical epidemiology describing the spread of a disease. So you've got two parameters, B and K, controlling the rates at which your disease infects people and either kills them off or people recover from it. And then you've got these different state variables representing the proportion of population in different, whether or not they haven't caught it yet, whether they've caught it or whether they've been removed from it. And then you sort of move between these different states according to this vector field over here on the right-hand side. But the thing is that what we're doing here, this is actually exactly the same thing as what I just told you, right? We've got these parameters B and K, rather than whatever the parameters we're using in the neural network are. But when we put these in, we see that what we actually have here on the right-hand side is a neural network. It's a very particular neural network. It's a very theoretically motivated design, but it's a neural network. And you can see I've gone and written it down at the bottom here. So you can see that this idea that I introduced a slide ago of neural differential equations of let's put a neural network in our vector field. Well, actually, that's what we've been doing all along since forever. It's just that rather than it being a theoretically motivated choice of this, because that is probably something that looks like how diseases spread. It's a different theoretically motivated choice of a neural network, with the theoretical motivations being neural networks are good at fitting things, they're high capacity function approximators and things like that. And of course, we don't have to stick to just ODEs. We can, you can look just basically anywhere in the mathematical modeling literature, and you'll stumble across something like this. Right? So this is an SDE example of the Hesston model for modeling asset prices, and it's exactly the same thing. The fact that there's an SDE doesn't change anything. We've got some parameters, and then we're gonna push them through some neural networks, what I'm going to call neural networks, and we get the same thing out. So what I'm trying to convince you of is that what I'm presenting here, it's not just like a mishmash hybridization that's been dreamt up by a grad student on paper ideas, but it's actually, it's really what we've all been doing all along anyway. So that's from the sort of traditional mathematical modeling side. If you're more of a sort of deep learning bent, if that's more your background, then if we just consider this neural ODE that I already wrote down, and then we solve with the simplest possible numerical method, that is to say, the explicit Euler method, then, well, that means we approximate our derivative just with a little finite difference like that, and then we rearrange. And then you see I've done this rearrangement. This is just these two equations put together, and what we have here is now the formulation of a residual network, which is I think probably like the most cited paper in the field or something. Which these are absolutely ubiquitous, and so we see that actually what's going on here is that a lot of many very popular neural network architectures are actually all discretizations of some neural differential equation, and at least to me, I think this is possibly why they work. Right, a lot of these neural networks work because they look like differential equations. You can find other examples for which this is true as well. And I think anyone doing traditional differential equation modeling is hopefully not too surprised, because of course we've been using differential equations all this time precisely because they work so well. So it's not a great surprise that the new kid on the block is actually doing the same thing behind the scenes. So what are the benefits of this sort of hybridization? Beyond it, oh, it seems neat, right? What are the practical benefits? Well, if you're approaching this from, as I say, the side of traditional mathematical modeling, then we've got these very high capacity models. I've not written down something that's very strongly theoretically constrained. I've written down something that can it's very flexible. It can take lots of forms. And they're very easy to train. And the fact that we're bringing this together with the neural networks with differential equations means that we don't have to replace traditional techniques. We can actually augment them, and we can sit alongside them. This is quite like a neat harmony between them. So we see that what we end up with is we get to do more or less what we were doing before, but now we can just do it better, basically, right? Because we get these stronger, higher capacity models. But if you're coming from the more machine learning side of things, maybe differential equations aren't what you're used to. Well, first of all, differential equations are good priors on model space. This is kind of what I was saying earlier. It's kind of why a lot of models seem to work. It's just a good way of understanding how the world is. They're able to handle things like irregular data quite nicely. They're often maybe more memory efficient because you can get invertibility properties. And if you're more of a theoretical bent, then as I say, I think this is sort of what gives a good theoretical understanding for why lots of neural networks work. So yeah, neural differential equations, clearly, I hope, very cool. Lots of different benefits. What are the practical applications? So I think there's three main ones where we're really seeing these things starting to get used. So the first of them is all the places people are already using differential equations, right? We've been using them, as I say, since forever, and now we can drop in a neural network to help improve things, and differential equations are always going to be a good choice here. There's generative modeling. I'm going to touch on neural SDEs a little bit at the end. This is a nice example if you're in that field. And then also time series applications are a very natural one as well, because here very often the data sort of have this evolution over time that we expect differential equations to mimic. So that was my, I think, 10-minute introduction to the field of neural differential equations in general. And I've been very deliberate trying to hit the high point, so hit the high level points without getting too far into the technicalities, and particularly without sort of really linking up with all this rough path theory that we're doing today. So at this point, I'm now gonna pick a particular example, the neural controlled differential equation. We'll get slightly more technical, and we'll touch on perhaps on a little bit on some of the connections to rough path theory as well. So first of all, let's just remind ourselves about that neural ODE I wrote down earlier. Here it is. I've written it down in integral form rather than differential form, but nothing else has changed. And then we've got this integral, and this is introduced, and then it's integrated over. It's just some internal detail of the model. If I'm sort of standing from the outside and I just hand the model an input and it gives me back an output, I didn't know that it did an integral to get there. But if in fact I do have some ordered data, maybe it's a time series, it's a sequence, it's a stream of data, then we're going to want to align, we're going to seek to align this integral with the ordering of our data. That feels like a sensible thing to do. But the problem is that this is an ODE. This solution is determined by its initial condition. So if I have some ordered data here, then great, I can make y naught depend on x naught. I've got a way of inputting x naught into my model, but I don't have a way to input x1 or x2 or any of these later ones. I don't have a way of reaching into my model and making that thing happen. So we want a way to incorporate this incoming information. So the good news is that we have this mathematics of controlled differential equations. This is the reason we're all here today. And this gives us a way to make this work. So what we're going to do is we're going to have this way of having the local behavior of the system depend upon an input. And we do it just writing down this equation. We've actually already seen this equation in some of our previous talks. Previously, that was dy equals f dx. Again, I'm favoring integral notation. No particular reason. It doesn't really matter. And we write it down like this. And then in integral notation, we're going to think of this as a Riemann-Stieltjes integral. And I don't know if people are familiar with this or not. I'm not too certain what our background is here today. But if you're not, then you can think of this as being, like as a very, very loose approximation. It looks something like this, where the first equation is a bit more sort of mathematically natural. It's kind of like the better way to approach this, like for various sort of theoretical reasons. But the bottom one kind of gets the gist across that we have this integral, and as time goes along, it depends upon what x does. So we're evolving forwards from time equals naught to time equals capital T. And as we do so, we have this x, and this x is going to introduce changes into our system. X is the observed data that we've looked out into the world and seen. This gives us a way to modify, this will modify what happens to y. So as I say, changes in x provoke changes in y. That's the really key idea here. So let's look at how we're actually doing that. We've got some time series. I look out into the world, I observe a time series. A time ti, I observe value xi. And then what I'm going to do is I'm going to join up these dots. And then that gives us this continuous interpolation of the data. If you're familiar with problems like informative missingness and so on, that can be made to work, but I'm not going to be touching on that today. So we join up the dots, we have this continuous representation of the data, and then all I'm going to do is I'm going to learn some functions that do kind of more or less what I was just describing earlier, where you can see that now what I've got is I've got this controlled differential equation over here on the right hand side, and it's we've got this neural network, and as changes in x come in, then y responds appropriately. We train f so that y responds appropriately, and then we're going to have some output from the model. I'm sort of not really getting into the details of why this works. I just want to get the intuition across that we've got input data x. As input data comes in, as we make observations, then that pushes changes in y via this controlled differential equation. And then we end up sort of then reading out for y to get outputs from our model. So that's like the minimum amount of structure. These are basically arbitrary neural networks like the feed-forward network we saw earlier, and y is typically what's called hidden state. And then as a picture, it looks something like this. So you can see we've got this process x. We make observations xi at time ti. We join up the dots to create this capital X, and then in continuous time, this drives changes in y. And if this is all feeling a little bit abstract, then this is now this is sort of the intuition for those of you from a deep learning background. This is directly analogous to a recurrent neural network that looks like this. If I have a recurrent neural network, then here in discrete time, I make an observation x, I have some hidden state y, and I update it to create my next hidden state. So that's happening in discrete time. This is happening in continuous time. And in fact, for any discrete time problem, I can write down a continuous time problem that it is the discretization of. So this is the sort of essential idea here. We're sort of what we're seeing here is that this is why recurrent neural networks work. So we call this thing a neural controlled differential equation. And this sort of time series, this can be any kind of time series, right? So this could be the position of a pen over paper. I think Terry had an example earlier about Chinese handwriting, Chinese character handwriting. This could be patient hospital records, so heart rate, lab results, and so on. It could be spoken audio, it could be weather data, it could be physics, and so on. Any sort of time series are kind of admissible into what we're doing here. And I think what's kind of nice at this point as well is to emphasize that very traditionally you write down differential equations that are theoretically motivated, right? You hired a mathematician, they sat down, they thought very hard, they wrote down this beautiful theoretical model for what's going on. But the approach that we're extending here is something which applies even when we don't have that theoretical understanding. Because I don't have a theoretical understanding of patient hospital records, I think that sounds like a hard thing to do. It's messy, it's complicated, right? But as long as we have data, I'm telling you, I can train a neural differential equation to understand what's going on, to give me a model of what's going on. So I think this is a nice way of extending the differential equations that we know and love to the problems that we can't even hope to theoretically understand. And so the advantages of this, I've sort of touched on some of these earlier. The advantage is that we've got this continuous time theory. This makes handling messy data very easy. This equation, the same equation I wrote down earlier, with a bit of sort of playing with it, you can actually treat this as a neural ODE, ordinary differential equation, so something without this sort of possibly unfamiliar looking dx at the end. And that means actually we can solve it using existing software, existing tools. I've not told you what this is, but as sort of I briefly touched on earlier, you can get memory efficiency in your model as well, which is often useful in many contexts. From the theoretical point of view, this is really helpful. We understand this neural CDE in very good theoretical ways because we have all this beautiful path theory we can draw on. And sort of conversely, because these are continuous time RNNs, this actually now offers a way to understand RNNs better as well. And finally, at the end of the day, do these things work? Yes, they do. And so I'm just going to give you a very, very brief example here. This is an example of some handwriting recognition, actually, where we compare neural CDs against a variety of other things like recurrent neural networks. And the short version is yes, it works as advertised. We get very good results. These good results maintain even when we drop large amounts of the data, and indeed they do so whilst using a lot less memory in the GPU as well. So I think that seems pretty good. So I've said the word controlled differential equations a few times. Indeed, I think many other people have said them a few times over the course of this talk. I don't know if this is worth stating at this point, but this is kind of similar to control theory, kind of. The usual difference that's made between them is that in control theory, the system F is fixed, and we try to find an optimal control that does what we want, whereas in this case, it's flipped around. Usually our input is given to us, that's given by data, and now we're going to learn an optimal system that does what we want. That's usually the distinction that's made, but I don't think it's a terribly important one. So I think I've got 2 minutes left, so I'm going to very quickly whip through a very final application of neural CDs, and as you might expect, in absolutely no technical detail. But neural STEs, we've decided we can do neural differential equations, and of course there's all sorts of differential equations out there. I've spoken about neural ODEs, ordinary differential equations. I've spoken about neural controlled differential equations. So yes, we can do neural stochastic differential equations as well. And what do? Well, we write down a whole smorgasbord of equations. We join them all up, and as it turns out, you can actually write down a neural STE here in the middle. We have a neural CDE again, so again, drawing in on all the stuff we've been describing so far here at the bottom. And what you do is these actually form what's called a generator-discriminator pair in a generative adversarial network. And what these do is that this actually gives a way now to learn an arbitrary STE. So maybe if you're doing, I don't know, financial modeling or something, you're thinking, oh yes, I like learning STEs. They are good models for finance. Well, I'm telling you that we can learn very flexible models, much more flexible models now, because they can be neural networks. They can be a lot more than just these theoretically motivated ones. So that's what I'm saying. In the infinite data limit, we can get any STE in theory. So I think we've really, by basically using pretty much the same theory, we've come a long way from the traditional techniques that are sort of, often much more familiar. But there's actually very little new going on here, right? It's a lot of this is just a reinterpretation of what's already going on. So do these work? Yes, they work. Again, short on time, but look, I've got so I've got histograms and line graphs and tables and things. Clearly, they work. Trust me, it's true. In short, they do. And the only one I want to highlight here is this Beijing air quality data set. I think this is really cool because, again, this is an example where I have no theoretical understanding of what's going on, but I can write down an SDE model for it regardless. So I think this is pretty much my final slide. So software, we've got standardized software for doing all of this. There's a low barrier to entry. If this is something that you're interested in using, then you've basically got two choices. There's the PyTorch ecosystem with TorchDFQ, TorchCD, and TorchSD for sort of each of these different flavors. And then if you're a fan of Julia, then there's the very comprehensive differential equations.jl. And these integrate into their larger ecosystems pretty much seamlessly. So they do all the things you'd like them to do. So as a quick summary, this is what I've been talking about. Differential equations, these are already ubiquitous. We see them everywhere. And neural differential equations are just taking this idea, just pushing it a little bit further. we're seeing widespread applications to traditional problems in finance, physics, engineering, and so on, but also to the more modern problems that we see in machine learning. So often in things like time series problems and things like that. And I think, to be honest, our main challenge at this point isn't the technical development of this theory, but simply to convince everyone else that they should be using these things too. And I think that's really the reason we've got this seminar here today, to try and convince people that, hey, this is really cool stuff, and this needs more people using it. So these are the main references for what I've been discussing here today. This is the links to the software. If you want links to these, I think the slides are being made available. And indeed, there's also an extended version of these slides available on my website. Feel free to reach out to me if you've got any questions later. I'm a developer, or at least involved with most of the major PyTorch libraries. Happy to talk about those too. And all that remains to say is sorry for going much over time. And thank you for your attention. And I'll take any questions.
All right, thanks a lot, Patrick, for your nice talk, and you were exactly on time. So
oh, exciting, excellent.
And we already have the first question, namely, could it be possible to use neural CDEs as priors or regularizers in convex problems?
I think that question would need a little bit more specification. That's.
I agree. Priscilla, could you maybe clarify what exactly you mean? Anyway, why maybe we could. Does somebody else has comments or questions, remarks?
So Priscilla says to solve inverse problems.
Oh.
So yes and no, I think is what I'd say. I think what I'm describing here is it's a way of approaching things that is in some sense the same as what people have been doing in mathematical modeling for centuries, because it's using differential equations in the way they've always been used. In some sense, it's the same as people have been using in deep learning for the past decade, because it's drawing on ideas that it's basically just a recurrent neural network, just with a differential equation instead. So what I'd say is that look to whichever of these two formalisms you're more familiar with. Can you make things work in that case? And if you can, then you can use the tools I'm describing here. And then in particular, can you solve inverse problems? Can you do regularizers? Use things as regularizers? Then that I think is sort of slightly more problem specific than I can answer in 1 minute over Zoom.
All right, thanks. And you are around anyway for the breakout session, Patrick. So in
Yes,
case
indeed.
somebody has questions, you are around. And let's see if somebody else has a question. If not, maybe let's move on to set up James.